Management and Decisional System. Forecasting. In this video, we'll present the forecasting in electric power systems, its necessity and forecasting methods. At the end of this module, you will be able to understand the importance of forecasting in electric power systems, understand the forecasting process, identify some forecasting methods. Everybody has heard about weather forecasting. Weather forecasts are made by collecting quantitative data about the current state of the atmosphere at a given place, and by using meteorology to project how the atmosphere will change. In general, a forecast is a prediction of future events based on past and current data. In addition to meteorology, forecasting is also required in many situations and fields, including business, industry, government, economics, medicine, politics, social sciences, etc. The reason why forecasting is so important is that predictions of future events are a critical input into many types of planning and decision-making processes. For example, governments, financial institutions, and policy organizations require forecasts of major economic variables, such as gross domestic product, population growth, unemployment, interest rates, inflation, job growth, production, and consumption. These forecasts are an integral part of the guidance behind monetary and fiscal policy, and budgeting plans and decisions made by governments. So, how are the forecasts made? It all starts with problem definition, where the purpose of the forecasts is determined. It requires an understanding of the way the forecasts will be used and by whom. Also, an important part of this phase is the definition of the forecast horizon. How often does the forecast need to be revised, and what level of forecast accuracy is required in order to make good decisions? The next step in the forecasting process is data collection. It consists of gathering the history of the variable or variables that are going to be forecasted, including historical information on potential predictor variables. The predictor variable is a variable which values are used to predict values of another variable. In our case, it's the forecast variable or response variable. For example, the effects of the total yearly amount spent on advertising may explain some of the historical variation of yearly sales and may lead to more accurate forecasts. Often, historical data is not useful for the current problem due to structural changes in the system being forecasted. Often, it's also necessary to deal with missing values of some variables or potential outliers. Sometimes data may not be available yet, if, for example, the forecast is aimed at a new product. In this case, the forecast is made by experts in the field. After obtaining the necessary historical data, a preliminary analysis of data needs to be done. The purpose of this analysis is to obtain some feel for the data. Data plots are usually used to reveal patterns, such as trends and seasonal or other cyclical components. Additionally, unusual points or potential outliers should be identified and flagged for possible further study. All this information can then be helpful in the selection of the forecasting model. Once all the data is collected and analyzed, we may then choose and fit the model to the data. It's common to compare two or more potential models. By fitting, we mean estimating the unknown model parameters, which must be estimated using the collected historical data, usually by the method of the least squares or the maximum likelihood. There are different methods for evaluating the quality of the model's fit. If the model doesn't fit the data, we go back to analyze the data again. Once a model has been selected and its parameters estimated, the model is used to make forecasts. It's very important to compare the results of the forecast model to the actual data. This allows us to evaluate accuracy of the model. It's necessary to distinguish between accuracy and fit of the model. By fit of the model, we mean fitting the model to the historical data on which model parameters are estimated. And by accuracy of the model, we are referring to when the model is used to forecast new data. A widely used method for validating a forecasting model before it's turned over to the customer is to employ some form of data splitting, where the data are divided into two parts, a fitting part and a forecasting part. The next two steps of the forecasting process are model deployment and monitoring forecasting model performance. Forecasting model is deployed to real data and results can then be used by the customer. The last step is an ongoing activity after the model has been deployed to ensure that it's still performing satisfactorily. Forecasting is an integral part of any sphere of human activity, and energetics is not an exception. In an electric power system, what is mostly forecasted is load, power generation, power loss, and electricity price. The operation of the electric power system requires consistency between the consumption and the generation of electricity, as due to the current available technology, electricity cannot be stored in large quantities. Load forecasting plays an important role in managing power systems, and is crucial for the stable operation of a power system. Load forecasting is also considered a critical factor for the economic operation of power systems. Accurate forecasts can hold a great saving potential for electric utility corporations. In conventional power systems, electrical energy is generated in centralized power plants and then transmitted and distributed through transmission and distribution networks to end consumers. Nowadays, with the recent integration of smart grid systems to today's power system and the increasing penetration of renewable energy sources like photovoltaics and wind power and electromobility, it all brings new challenges for the power system planners. Photovoltaics and wind power play an important role in minimizing the shortage of load and in providing clean energy to the power system. However, due to the uncertainty of the solar radiation and wind and of the changing weather conditions, it makes it difficult to manage these renewable sources to feed the power system. An unbalanced power system can cause huge damages. Therefore, forecasting has become a key tool for the optimal, secure, and reliable operation of power systems. With respect to the time period or forecast horizon, there are 4 types of forecasting. The first is the short-term forecasting, which is an essential tool for the control and efficient operation of the power system. It helps to make important decisions, such as related to purchasing and generating electric power, load switching, security assessment, and many others. It's used for forecasts for 1 hour until 1 week ahead. Then there is the medium-term forecasting, which is applied to the maintenance scheduling or fuel supply planning. It's used for forecasts for 1 week until 1 year ahead. Long-term forecasting has an impact on issues such as strategic planning and expansion of the power system, determining the economical location, type, and size of future power plants and transmission lines. It's used for forecasts longer than 1 year ahead. Finally, there's the very short-term forecast that's essential to ensure the secure and economic operation and the grid energy management. It's used for forecasts for a few seconds to 1 hour ahead. It's mainly used for forecasting photovoltaics and power wind generation. The forecast horizon is the number of future periods for which forecasts must be calculated. For example, in purchasing electric energy, load forecasts may be made on a daily basis. There are a variety of methods for forecasting. Despite the wide range of methods, there are only 2 broad types of forecasting techniques: qualitative methods and quantitative methods. Qualitative methods are often subjective in nature and require judgment by experts. They are used in situations where there is little or no historical data on which to base the forecast. The most known representative of this group is the Delphi method. Quantitative forecasting methods use historical data and a forecasting model. In the literature, the quantitative methods are commonly grouped in 2 major groups: statistical methods and artificial intelligence methods. Statistical methods require small sets of input data when compared to the AI methods. As more sets of data are used, more accurate will be the AI methods. Hence, the more effort is required for the computation of power output. In comparison to statistical methods, AI methods have the capability of learning complex nonlinear relationships, which are difficult to model and thus make them popular. Some widely used statistical methods are linear regression, multiple linear regression, time series methods, or ARIMA models, exponential smoothing, among others. In the AI group, there are also various methods such as artificial neural network, or ANN, support vector machine, or SVM, genetic algorithm, fuzzy logic, among others. As we can see, there are several existing methods. So the question is, which is the best method to use in forecasting? The selection of a method depends on many factors: the context of the forecast, the relevance and availability of historical data, the degree of accuracy desirable, the time period to be forecast, the robustness of the method, the cost, benefit, or value of the forecast to the company, and the time available for calculations and making the analysis. To summarize, these are the key takeaways from this video. Forecasting is an integral part of any sphere of human activity, and energetics are not an exception. Forecasting in electric power systems is crucial for the stable operation of the power system. Due to the dependency on weather conditions, forecasting of photovoltaics and wind power generation and other distributed generation play an important role in the interconnection of the distributed energy resources to smart grids. Thanks for watching.